actually be a source and this will actually be a sink. Because if you start any flow line here, it's going to tend to flow down in any direction, no matter what. And if you start here, things can flow to it. You cannot flow outside of it because this will be a sink. So there is an inherent difference. They are both critical points, but one is a source, one is a sink. Here, this is like a source, this is like a sink. But you see here, there are differences, right? Like along these directions, things are going to flow in, but along these directions, things are going to flow out. So this is not the same as this, and this is also not the same as this. It's just locally. Okay? So we have to capture that by assigning it an integer, which will come through by the edge here, so that it's a well-defined quantity and so on. So we have to keep track of that as well, not just critical points, but these integers, because that tells us what is happening when I go from here. So, okay, so right now let me just write down those integers and explain why they are 2 and so on and so forth and so forth. 0, 1, 1. And for the time being, think of it this way. There is a whole 2-dimensional what of direction that and all. And no matter which direction you choose, things are going to flow. Whereas here, no matter which direction you choose, things cannot flow down. It's already at the lowest point. Here you will have exactly one direction which will flow down, into this direction. The other direction can only flow into, cannot flow down. So anyway, we have this thing. So here, okay, so you can think of it as a point. I'll just see there are a lot of identifications that one has to do. So I'll pretend we are doing it. So when I use this symbol, this one, this means what of the equivalent. Okay. So if you haven't heard of what this is, it simply means it's not as strict as homomorphism. You are allowed to have two spaces being homotopy equivalent, meaning that there should be a map F from X to Y and a map G from Y to X. The F compose G is connected to the identity by one parameter family, and G compose F is connected to the identity by one parameter. So there need not be strict inverse relationship. So I in topology quite often want to work on that. So this is the same as a point, okay? Meaning this particular point. And one way to see this is you know that if you take a disk, you can radially deform the disk to the center. And that is a homotopy. So this is the same thing as just the base point itself. Whereas here, I'm going to draw it slightly differently. So this is what I originally had over here, right? Now I'm going to draw something different. Hopefully you can. It's like a yellow band, but you can only see half of it. The other half is actually on the other side. So you take this disk, imagine you wanted to build this, but not through this picture, but through some control topology. So what you could do is you could almost like creating a basket, right? So you're just attaching a handle, and this, for all you care, is basically an interval. It's just an interval I've colored it yellow and I've attached it to this picture, but topologically it's an abstract quotient space. And you have this disk, identify 2 points, like so, and then you attach an interval with the endpoints identified this way. So I could actually have attached a thickened version of this. Instead of attaching this, I would have attached something like this. And still it would be the same thing. So this now is not because I've changed the topology. It's like say if you started with a point and then you attach an edge to a point, it becomes a circle. It's no longer the same thing as a point, right? But if you look at this, like a basket versus this one, are they equivalent in this motion? You think that you can deform one to another? So you could try, right? So here, essentially what are we saying? We're saying from this, imagine you attach like a pattern handle like this, right? So now all you have to do is you have to start pushing these things all the way down to this. Start pushing those. So this cylinder is actually this, because if you think of it, this is also a cylinder. Because what are the boundary components? This, right? That's one circle, and then we have another circle and another circle. the space, the surface which has two circles. So is the cylinder, this is oriented, this is oriented. This is actually a cylinder, and a physical way to go from here to here, you basically push everything down to this, and then you can push the thickening down to the single thing. So you can go from here to here by attaching this edge, which will be calling a one handle or a one cell or a one interval. Now, how do you go from here to here? You sort of from here to here. Yes. So I'm saying I started with the disc and attached this one single thing. I can thicken that. None of this changes the look of the type. But I'm saying this object, the disc with this thickened handle and this thing are out of the picture. And I'm claiming that because I'm saying I can deform this to a picture. So what I do is I basically start deforming this down this. So because if you look at this shape, so it's basically a cylinder. I can just deform a cylinder along the vertical lines from the outer cylinder to the inner cylinder. I can do the same thing. So I can obtain this up to homotopy, not the actual geometric object, by essentially keeping track that I take this disc, which is secret here point, and I'm attaching an interval. So this is what Morse will essentially give you once you develop full field. But in this example, we cannot stop here. We have to also say what happens when I go from here to here. Is there a similar thing going on? So yeah, so now as some of you are pointing out, you see here we sort of attach this one. Here you see you cannot attach it this way. With the directional zero, no way you can attach it across the board. You can attach it this way. It's kind of forced on you. And you'll see why the directions change. Directions change because again they are both of index 1, but they have different structures. When you write down this map H in terms of its two local points. This is not a function defined on x1. This is a function of x and y locally because it's a surface. So here you want to attach and some of you are pointing out something like this. So this and this should be perpendicular. Again, if you thicken, what do you do? You get something like this. Right? Okay. So I'm attaching this, but I'm imagining I'm attaching a tape rather than a single strand. Again, the same question. Do you believe that this and this are the same in the sense that I deform this? So for those who haven't seen this or may not be that visually keen, this may not be immediate. It's good to go back and just imagine these things a little bit. Convince yourself that okay, we are not doing something entirely uniform. So it turns out you can deform this to this. Again, the same reason. You can start thickening these, or you can start pushing these things down and get this. Now, how to go from here to here? Well, that's pretty simple. You take a cap. It's like you have a lid, push the lid up. Then you close the lid, and then you're done. Then there's nothing. So you sort of start off with a point, which is taken to a lid. You attach a one handle or an interval, you thicken it, you deform it, and then you attach one node to the opposite order. And then you attach a lid and you build it. So you want to capture all of that, not by picture, because this is of course not proving anything. But it's giving you a glimpse of what a suitably nice function and with a control over what happens when you go through the critical points quite easy. So the index of the critical point, when you pass through it, tells you what kinds of things to do and where to do them. You cannot just do them randomly at any point. Okay. So, any questions? Yes.
How can we go from M1 plus epsilon to M minus? From third figure to the second figure, and then the first.
From here. No, so I'm saying you can go. So I okay. So then this, and then we have this, right? Right? So this was the original figure. I'm saying we'll go from here to here. We attach it, this. So you take this, you attach an interval, and then if I thicken this interval, it becomes like this.
This one, can we go from that one to the that
it's in two steps, right? You go from here to here, and then you go from here to here by attaching this. So this picture, the current one that I've drawn, is according to this notion of homotopy equivalence, they are homotopy equivalent. They are homomorphic, but you can deform this. And if I erase this, I can obtain the cylinder from this, and that's what it do. So it's a stepwise thing. So if you ask, can I go from here to here, I will show you 2 steps according to this algorithm. Because you are passing through 2 critical points. You have to handle each one separately. And it's best to handle them separately rather than handle them simultaneously. You can also have them together.